Our third shuffle for today is Shuffle 31, which is also a judicious push-off pairs. So let's go ahead and illustrate this shuffle and derive the permutation associated with it. So we begin with the ordered packet 1 through 8, and we perform the shuffle. Recall, a push-off pairs is where you just push off the top cards without rearranging the relative order and just set them down as one pile. Push off the next two and just set them down as a second pile. The next two as a third, and then the final two as a fourth pile. And that's how we number the piles, 1, 2, 3, 4. Now the stacking this time is we're going to use this leapfrog stacking. We're going to leap over the neighbor of one pile and land on another pile. So here, if we read the notation, pile 4 will be set on top of pile 2, pile 3 will be set on top of pile 1, and finally, given those two piles, we will stack the right-hand pile on top of the left. So that is this new shuffle here. Okay, so let's go ahead and do it. Use this leapfrog. 4 goes on top of 2. 3 goes on top of 1. And then we're stacking the right pile on top of the left. So what is the new ordering for this packet? And what would the Cauchy two-line notation be for this permutation? So the new ordering is 7, 8, 3, 4, 5, 6, 1, 2. So in Cauchy's two-line notation, we obtain the following. We begin with the top row, of course, just being 1 through 8. And then the second row will be the new ordering that we just found. 7, 8, 3, 4, 5, 6, 1, 2. So that is Cauchy's two-line notation. This two-line notation can be converted to cycle notation, also called one-line notation, as follows. We just look at what happens with each position. So 1 goes to 7, so there's an arrow from 1 to 7, and then 7 returns back to 1, so it cycles around. So we get this 2 cycle, also called a transposition. What happens with 2? Well, 2 goes to 8, so we have an arrow from 2 to 8, and 8 returns back to 2. So we get a second transposition, or 2 cycle. Now, 3 gets sent to 3, so we have a fixed point. This is also called a 1 cycle. 4 goes to 4, it's also a fixed point then. 5 as well, and 6 as well. So that accounts for all 8 digits. Now I do want to remind the viewer that normally when we write a permutation in cycle notation like we have here, we don't include the 1 cycles, the single cycles, as long as it is clear as to the size of the set we're working with. So as long as we know that we have 8 distinct objects, then we can drop these 1 cycles without losing any information. So in other words, what it means is any number between 1 and 8 that's not present here in either transposition would have to be a fixed point, which they are. If we color code our position digits, we obtain the following. Remember, the positions 1, 4, 6, 7 are color-coded black, and position values 2, 3, 5, 8 are color-coded red. And this aids us in discerning what effect a particular shuffle has had on the underlying Bessey sequence structure. The two cases being that it returns the sequence to the same form of the Bessey sequence, or it converts it into its inversion. Okay, so we see that black 1 goes to black 7, which returns to black 1. Red 2 goes to red 8, which returns to red 2. Red 3 gets assigned to itself. Black 4 gets assigned to itself. Red 5 gets assigned to itself. Black 6 gets assigned to itself. So here we have the following. Each value gets sent to a value of the same color. So we do not have an inversion of the sequence in this particular case. So what that means then is if we start with our quintessential Bessey sequence of 1 0 0 1 0 1 1 0 and perform this shuffle, we should get that sequence form back. So why don't we go ahead and perform it again. So I'm just pushing off the top 2, setting those down, pushing off the top 2, next 2, and the bottom 2. The stacking, as we see here, so we're picking up the 4th pile first, is leaping over the 3rd and landing on the 2nd. Here we pick up the 3rd pile, if I can get underneath it, and it jumps over the 2nd and lands on the 1st pile. And then here we're stacking the right pile on top of the left. So what should happen here is we should get back to the same sequence organization, namely 1 0 0 1 0 1 1 0, and we do. Now it is important to realize that some of these cards labeled with a 0 or a 1, some of them have stayed right where they were and others have moved, even though it's hard to tell because we have the same labeling. So in particular, the cards originally in the 1st position and the 7th position, this position and the 1st position, they've switched places. The cards originally in position 2 and 8, way over here, those have switched places. All of the other cards have stayed where they started. So in this case, we would say that this shuffle preserves Bessey sequences. And what that means is, if you start with a Bessey sequence of this form, you end up with a Bessey sequence of this same form. 1 0 0 1 0 1 1 0. We can see that since this shuffle is a product of transpositions, it has order 2. So performing this shuffle twice returns the packet to its original order. And if we look at the shuffle diagram for this shuffle, we find the following. Because 1 and 7 constitute a 2-cycle, we should expect to see a double arrow between 1 and 7, which we do. Also, the transposition or 2-cycle 2 8 would lead to a double arrow between 2 and 8, which we have. All of the other values have been left as they are, indicating that they are fixed points. The objects in those positions are returned precisely to those same positions, so they do not move anywhere new. And we can see right here that inversion does not occur.